Okay, hi all. Welcome to the session 9 of Science at Low Frequencies 7. This is on the solar and the ionosphere. Folks are still kind of streaming in, but let's get started. We have 5 wonderful speakers for you today. One invited speaker and 4 contributed talks. As for all of the sessions, you can add your questions at the Q&A in the Q&A button tab. Please add the name of the speaker at the start of your question so we know who it's directed towards. If you prefer to wait till the actual question and answer session and answer your question directly, just raise your hand and I'll unmute your mic during the Q&A session. There will be a coffee session afterwards, as always, and the link for that is also in the PDF that was circulated via email. I want to also just mention the lightning talks again as an option because it's a great option for those of you who want to get your results out there. There are about 13 or 14 lightning talks already up there and they're racking up the views, so please do that. The discussion can also happen via the Slack in the solar_ionosphere channel, both during the session and afterwards. So let's go ahead and get started. So first up for our invited talk, we have Sherry Chahabra from NGIT and NASA Goddard. Sherry, you have 25 minutes for your talk with 5 minutes for questions, and I will give you a 5-minute warning.
All right, thank you, Greg.
You can go ahead and share your slides. Yeah, okay, it's all yours.
Yeah. All right, can you see the screen now?
Looks great. You're good to go.
Perfect. Hello, everyone. So today I'm going to talk about the radio properties of the sun. In particular, I will give a review of different radio bursts associated with impulsive events, what their underlying mechanisms can be, and how they help better our understanding of the fundamental processes that drive the solar coronal emissions. All right. So impulsive events on the sun can occur in the form of jets, erupting prominences. For example, the one that I'm showing here, prominences are filament-like structures that are anchored to the surface of the sun, and they consist very hot ionized plasma. The one that do end up erupting and are not stable may spew a lot of material out into interplanetary space, but most of it does end up falling back on the sun. The stable ones can actually persist for a few weeks, even months sometimes. More energetic phenomena are solar flares, which are the largest explosions in the solar system and can produce up to 10 to the power 32 to 10 to the power 33 ergs of energy in minutes. Here, I'm showing an example of one of the largest flares that was recorded in the last solar cycle in March 2012. Just to give a quick lay of the land, how are solar flares produced? So the convective motions on the photosphere of the sun basically churn the magnetic field around. And as these loops get twisted and braided, they become really stressed. And the excessive tension causes a break in the field lines. This happens via magnetic reconnection around here in this region. And below you see the reconnected field lines. Up here are the field lines that are going inward due to pressure, the negative pressure. Basically, what's happening is as soon as you have first reconnection, there is outflow of particles, energetic particles, up here and down there. So that creates negative pressure, which drives an inflow of the other outlying magnetic field lines, and it drives the reconnection forward. Now, up here, what you see is a flux rope that is going across the active region. And as the outflow of the particles increases, this magnetic flux rope is driven out or ejected out, and it escapes into the interplanetary space as a coronal mass ejection, which looks something like this. So here is a movie of a coronagraph, and the flare right here has produced the ejection of the flux rope, and as it moves out into the interplanetary medium, you see that beautiful material spewing out. All right. Now, quite a few instruments have come online in the past decade or two that, although not solar dedicated, can be used to image the sun during such events and also during quiet times. We mostly do that to understand the radio emission and their underlying mechanisms. At high frequencies, we have EOPSA. This is a solar dedicated instrument, observes between 1.5 to 18 gigahertz. And it has, for the first time, also started producing daily images of the sun. So between the bandwidth of 1.5 to 18 gigahertz, it images sun at hundreds of frequencies every day. Then we have VLA, which images the sun at multiple different bands. These are the main ones that I'm showing only relevant to the sun. VLA also, although not solar dedicated, can image the sun at multiple bands. Also has an instantaneous bandwidth of 2 gigahertz, so it does not have to sweep along the thing, and a very high cadence of just a few milliseconds. All right, at low frequencies, more importantly, we have quite a few great instruments, all with solar imaging capabilities. To start, we have MWA in Western Australia that sweeps between 70 to 300 megahertz. Then we have long wavelength array in New Mexico that goes between 10 to 88. LOFAR in Europe that has 3 different bands, low frequency and slightly higher frequencies. And then we also have Owens Valley long wavelength array in California, sweeping between 25 to 88 megahertz. All right, moving on to different solar radio bursts associated with impulsive events. Let me go through a quick overview before I jump onto actual observations. So based on their appearance in the dynamic spectrum, which is basically an intensity plot as a function of frequency and time. The radio bursts at metric frequencies, metric wavelengths, are divided into 5 classes, type 1 to 5. Between these 5, type 1, 2, and 3 are basically characterized based on the drift that they show in the dynamic spectrum. So type 1 bursts are essentially, as you see them here, type 1 bursts are essentially spikes of enhanced emission that last about a second or less. They're mostly found in groups, so that's why it's shown as quite a long emission in time. But mostly when they're found as groups, they're called as noise storms. Due to their high polarization, they're attributed to being produced by plasma emission, although we do not really understand what accelerates the electrons that produces these type 1 bursts. The very important characteristic about these bursts is that they are quite narrow band, so they do not really sweep a long band of frequencies. At the same time, they do not show very much of a drift, either very little or none at all. There have been some very recent few observations that have observed drifts in type 1 storms, but more or less, I think that's just 1 or 2 observations the past 2 solar cycles. All right, type 2 bursts, on the other hand, that we can see right here, have been observed in association with coronal mass ejections. They exhibit a slow drift in the spectrum. So from high to low frequencies, you will see them moving along in the order of a few tens of minutes. They are believed to be caused by accelerated electrons from MHD shocks. These shocks could be produced in flares, jets, or even X-ray jets, or the front of the CME. But statistically, more often than not, type 2 bursts are seen in association with the leading edge of the CMEs. Type 3s, seen right here, are the fastest moving bursts associated with accelerated electron beams that again move along open field lines. I will talk more about these bursts in detail a little bit later. Then we have type 4 bursts, which are continuum emission that come in very distinct varieties associated with different phenomena, different emission mechanisms. The two important categories that we mostly talk about are moving type 4 bursts and stationary type 4 bursts. Stationary bursts are more common and they're mostly associated with solar flares. Moving type 4, on the other hand, are characterized by the upward moving continuum emission, and you obviously need imaging capabilities to be able to detect them. In the last solar cycle, we have only seen 4 reported cases of moving type 4 bursts, so they're quite rare, at least the observed ones. Emission mechanism, on the other hand, for both of them is quite unclear. It is generally attributed to gyrosynchrotron emission or plasma emission or even electron cyclotron maser emission. So mostly attributed to happening through electrons that are trapped in magnetic field, erupting magnetic fields. All right, last but not the least, at higher frequencies, we have microwave bursts and decimetric continuum. They occur largely due to gyrosynchrotron emission, which means they give quite, given good imaging capabilities, these bursts can really be helpful in understanding the magnetic morphology of the impulsive burst that we are looking at. All right, so let's look at some examples now. We start with microwave bursts and decimetric continuum for higher frequencies. Here is an excellent example of a very large flare. Excuse me. Observed in 2017. So to the right here is a cartoon overlaid with a standard solar flare model, just to show the comparison between the flare actually observed. Now, again, just like I said before, reconnection occurs here in the current sheet, and then particles, energetic beams are spewed both upward and downward. The downward moving electrons, which are highly energetic, give you hard X-ray emission, and the upward moving can give you radio emission and emission at other high energies as well. But along with that, they emit at a wide band of radio frequencies. So at somewhat higher bands in IOFSA, here is a beautiful example of the emission at multiple frequencies during the different phases of the flare. So on the left, I show the dynamic spectrum from IOFSA from 2 to 18 gigahertz. And here, right here, where the red emission starts, is the early phase of the flare and the main peak, which corresponds to also the hard X-ray peak in GOES and RESI. And then towards the gradual phase of the flare, you see more continuum emission. To the right, we show the same, but imaging done for all different frequencies. So here you can see the color scale shows lower to higher frequencies overlaid on top of extreme ultraviolet images of the flare. So what I really want to note here is that for specifically the main phase of the flare, you see as the particles are moving down from the reconnection, they really get collected on the loop tops of the already connected loops, and they show really high emission at higher frequencies in IOFSA. So, and then at the gradual phase, you see more emission towards the foot points of the larger loops, or so this one is actually suspected to be the flux stroke that I mentioned before, but it's still under conjecture. But more importantly, since IOVSA can image these bursts at hundreds of frequencies between that bandwidth, and it can do it every second, it gives us the capability of getting spectra for gyrosynchrotron at every pixel of the IOVSA images at each second. So here I'm showing an example of only one time at 1554, and we have just taken 4 pixels at during the gradual phase of the flare, and we here in the center show the gyrosynchrotron fits for each of these separate pixels, and what that gives us is magnetic field estimates for each of them. We can also, given the automated fits for gyrosynchrotron, obtain non-thermal densities and as well as the power law indexes for each of these times. So it's a very beautiful capability that we are now able to use. So, all right. Okay, moving on to plasma emission. Let's look at bursts of type 3, the ones that show higher frequency drifts. So here's a sketch of what happens. Basically, for a traditional type 3 burst, say you have a reconnection event occurring somewhere in closer down here. As the particles are thrown out, they traverse along these open field lines. And since these magnetic field lines have a density gradient that is from down in the photosphere to as you move outward into the interplanetary space, you're moving from higher densities to lower densities. The particle beams basically create two-stream instability, which produces Langmuir waves, and you have plasma emission at the local plasma frequency. So from higher densities to lower densities, you get emission exactly the same as higher frequencies to lower frequencies as particles move out into interplanetary space. And this very drift is seen as these vertical straight lines. All right, so now here is an fine example of a jet eruption from November 1st, 2014. And Chen et al. Used VLA observations to image these bursts. All right, sorry. Okay. So here I show a 3D version of the spectral image. So basically, the Y and Z are X and Y, basically the spatial coordinates. And here, this is the axis for all the frequencies. So each frequency basically is a slice, and you're just stacking them together from high to low. Now, if you look at the same thing, but overlaid on an extreme ultraviolet image, you can see the movement of the electron beam. So on the right here, I'm showing, so basically what I did was overlay them, the contours here, zoom in and rotate the frame for better visualization. What we see here is a quite beautiful progression of frequencies as we are moving out from the jet. Now, the best part about slightly higher frequencies is that since you are able to resolve the source, it is very easy to image the centroid positions and completely track the electron beams as they're moving out from wherever the reconnection site may be. So here what we are showing are different colors in time, which basically shows fragmentation of electron beams. So basically, from one point, you're seeing different electron beams moving out. And the same thing is shown in the bottom, but now with changing density. So that shows you that very close to the reconnection site, you have higher density. As you move outward, that's lower density, and that's the signature of a type 3 burst. the most beautiful outcome of this is that as you connect them back, you can literally point out the reconnection site. All right. So moving on to slightly lower frequencies, we have work from Macaulay where they looked at type 3 bursts at 3 different dates. And what they did is, again, used 50% contours of different frequencies between 80 to 240 megahertz from MWA and plotted them in context with the EUV and white light images. Now, what this does is basically gives you, once you can track the centroid positions of frequencies along the progression of the burst, you can basically create a height and density plot, which is what they create here. So they then compare it with the other models and different observations of density profiles for corona. All right, moving on to type 4 bursts. Like I said before, type 4 bursts are continuums, mostly seen in broadband frequencies. So let's just move on to the example. Okay, here is a flare from September 20th, 2015, which was also associated to a CME. That looks something like that. All right. So this CME was then imaged by OVRO LWA, which is one of the first light data for OVRO. So here I'm showing a movie. On the left panel is LASCO coronagraph with contours overlaid from LWA. And the progression of the movie shows the complete event, that is before the onset of the flare, during the peak, and right after. Here is one source that we identified in this complex radio burst, which basically showed sporadic different bursts happening during the main peak of the flare. After which, we had a second source that showed outward movement, which I will talk about in more detail in a second.
Sherry, 5 minutes.
Sure. Okay. And finally, I have here a third source, which is seen during the gradual phase of the flare. All right. So in the composite dynamic spectrum, here are the type 3 bursts that we were seeing in the initial phase of the flare, again, corresponding to the source 1 that we saw. The main phase of the flare, which is also showing more complex type 3 bursts, are also associated with the same region, and they come from this previous structure that was already present before the CME started for us. So this is a previous CME. We believe that there has been an interaction between the open field from the CME and the flare structure or the erupting structure, which gives you more of an open field for particles to move out. For the main source, the emission comes from here. This composite dynamic spectrum shows quite a lot of emission right here, which is not seen in the Riston data, simply because of the higher sensitivity of LWA. So this is the source now that I'm going to talk about. We see quite a lot of outward movement in this source. So what we did was try to understand how it moves outward and what are the association of the burst, what could be the underlying mechanism. So here is a plot on the left side where I am showing 50% contours of the LWA frequencies, and the slit is basically what we use to measure the height. Since it is a very convoluted source, we could not use the direct centroid positions, and we end up using 50% contours and then calculating a centroid position from that. Once we do this procedure, what we find is that for most of the frequencies observed, the outward movement is associated with the core of the CME. So now to understand what would be the underlying mechanism of the burst, we basically do a reconstruction of the CME. So we model a framework for the CME and then render Thomson scattering equations to understand the emission. By comparing the brightness of the white light CME, what we can get is an upper limit on the estimate of the density in that region. So once we did receive the estimate of density, what we realize is that the density is not low enough to completely rule out plasma emission, but not high enough either. So we then look at other measures. What we realize is that the emission is really smooth in all the frequencies that we are seeing, and comparison with microwave data shows a very low height for the emission, which tells us that gyrosynchrotron is a more plausible mechanism for the source. So here we perform spectral fits and obtain the physical parameters as the source is evolving. What we did was only take 3 times where we could correctly identify the source without any convolution with others. For that specific time, we perform the fit and obtain the magnetic field, non-thermal density, and the power law index. So what we see is that as the source evolves, the strength of the magnetic field declines, and so does the density. And as the source expands, the power law index also hardens. All right, so moving on to just last part, taking a very different tack, I would just want to show type 3 bursts observed in solar wind by the Parker Solar Probe. Here is one example, and what we're trying to do here is look at 2 frequencies, one over here in the upper band and one in the lower band. And the idea is to be able to identify a time lag between the 2 frequencies. So we do that with something called the time lag technique. All right, so here the time lag technique was first developed for extreme ultraviolet channels. What they have done here is simulated emission for different channels in extreme ultraviolet, but the technique cross-correlates these different channels as a function of imposed time lag. And the position where the cross-correlation maximizes, that gives you the lag between 2 frequencies. So this technique was developed to understand heating and cooling trends in EUV data, but we use the same thing for radio frequencies to understand moving particles. So when you have light curves like these for different frequencies in radio, where you cannot really understand if there is a lag between 2 frequencies, we basically use the same technique. So we make sections and cross-correlate one section of one frequency to another. And where the cross-correlation maximizes, that gives us the time lag between that pair. So using that, we identify time lags between these 2 frequencies over here as 14 seconds. So this was just an example that I wanted to show of a single burst. More importantly, we wanted to do this for type 3 storms and quiet regions where you cannot really see any emission, to understand if there are any ubiquitous type 3s occurring from reconnection events that are going on in the solar wind or also in the solar corona for that matter. So this example again, I have those 2 frequencies, and the time lag shows very nicely a peak at 14 seconds, which is quite visible even in the light curves. But more importantly, what it's showing on the sides are 2 bumps, which basically correspond to these, I should say, pseudo-periodicities. I mean, they're not really present, but since you have some bursts that are really just very closely attached, you see a pseudo-periodicity also identified by the time lag technique. What we did not find, though, was any ubiquitous presence of reconnection events showing type 3 bursts that may not be visible by eye, but still be in the background as radio haze. So I think that could be attributed to a lower sensitivity. So I'd like to look at more sensitive data to understand that specifically. So to summarize, with impulsive phenomena, it is a new era for radio observations. We can observe magnetic fields, understand non-thermal density, power law index, how the behavior of the impulsive events are. Type 3 bursts can show you ambience density and understanding of how the particles are accelerating. If you're looking at nanoflares instead, it can be used to understand whether they are efficient in accelerating particles or not. Type 2 bursts, which I could not talk much in detail about, can also be used to understand shock locations at the fronts of CMEs and the morphology. For solar wind, from the data, we do not see any visible signatures of ubiquitous reconnection. So we should probably be looking at maybe solar orbiter, which has a slightly higher sensitivity and a better cadence. All right, thank you.
Okay, thank you, Sherry. That was awesome. I hope my applause will do instead of canned applause. Okay, we have time for just a quick question or two. One in the Q&A from Harry. For the overall LWA event, from the dynamic spectrum or the height time plots, it isn't very clear if it is a stationary or moving type 4. How was it concluded to be the latter?
So basically, we looked, we did a very good examination of the movie. And so I understand that at the lower frequencies, it's not very clearly visible, but at higher frequencies, there was a very clear association of the frequencies centroid with the core of the CME. And we see the same movement even in the movie when we are comparing the LWA with LASCO data.
Okay, very good. Any last very quick questions? If you can raise your hand if you want to ask it live or put it in the Q&A. Okay, if not, we are actually at the 30-minute mark exactly. So I'm going to ask you to stop sharing your screen. And next up, we have Richard Fallows from Astron, who is going to talk about the scintillating tail of Comet Neowise. Okay, Richard.
Hey, thank you very much indeed. Let me see if I can switch around a little bit and share the screen. This is a bit better.
Okay.
Okay. Okay. Well, from my end, very good early morning from the Netherlands, and my name is Richard Fallows from Astron here, and I'm going to be telling you a little bit about the scintillating tail of Comet C2020 F3 Neowise, which was gracing our skies back in the middle of the summertime, at least for us from the Northern Hemisphere, where if we looked out very late in the evening after sunset, we had a pretty spectacular view of the comet passing across the skies. So this tail all started on Sunday, the 12th of July, when Kay Spasser, a colleague, sent an email to me saying, well, it's a crazy idea. How about trying to look for a pulsar passing behind the comet tail and look for deep variations in the dispersion measure or rotation measure? I didn't find a pulsar, but it did get me looking and thinking about the possibility of finding an interplanetary scintillation or an IPS source. And I happened to find one, which was 3C196, which happens to be LOFAR's best observed radio source, excellent scintillator, and it would be passing behind the comet tail with a separation from the comet of only 0.43 degrees, that coming Thursday, the 16th of July. So that meant a fairly quick scramble to get a proposal together and approved. And the International LOFAR Telescope Director, René Vermeulen, received the first of his holiday interruptions for that particular week, and very kindly granted us 5 hours out of the 4 hours of observing time that we had requested. So our aim was fairly simple. Basically, can we detect any intensity scintillation due to the plasma tail? Can we detect any refraction due to the plasma tail? Now, the literature on these subjects is actually pretty mixed. There are some observers which detect enhanced scintillation and enhanced refraction due to the comet tail. And there are others who have taken a look at comets and said, no, we don't see anything at all. So our idea was fairly simple also. Just observe 3C196 for the full 5 hours we'd been granted, centered on the comet conjunction, and basically use everything we could possibly throw at it using the LOFAR telescope. So that meant doing fast imaging, sub-quarter of a second integrations with the full international array. With the aim of can we detect any source position shifts due to the plasma tail? Also record simultaneously beamformed dynamic spectra from each international station and use those to both assess the solar wind conditions at the time using interplanetary scintillation, but also see, can we detect enhanced intensity scintillation from the plasma tail? And if so, how does this differ from the background IPS? So it should be straightforward, bit of tinkering, just run a couple of tests the day before to establish the exact observing setup, and everything should be fine, right? Well, there was a stop day beforehand, a stop 2 days beforehand, in fact, when they were doing regular maintenance on the system. That managed to break everything, including the scheduler, and it wasn't fixed until about 3 hours before we wished to start observing, which was not very much time to test the system and try and confirm that what we wanted to, the observing modes that we wanted to run could actually be done. And on top of that, I was actually traveling that afternoon en route to Norway. So another colleague, Michiel Brentjens, who's the chief breaker of systems at LOFAR, very kindly spent the afternoon coordinating test activities. And it did turn out that our observing mode that we proposed was a little bit optimistic and a little bit beyond LOFAR's current capabilities. And we were basically exploring the outermost edges of the correlator's power, and it wasn't quite enough. So it's as I was boarding the plane and really quite an hour into when we should have been observing already, that Michiel gave me the final decision. We can't do both. So do you want beamformed or do you want imaging? And so I said, for this, imaging as fast as you can. So we imaged across the band, 110 to 190 megahertz, 400 subbands, 16 channels per subband, and 0.167 seconds integration times with the full international array. Now that left me with as a beamformed person with a little bit of a quandary once we'd taken the data, because actually I wanted beamformed data to take a look for the intensity scintillation from each station. But what we had was correlations. So the next issue for me was really how to extract autocorrelations from all the data, as the LOFAR pipelines were never particularly designed for that. And it took about 2 weeks of trial and error, quite some cursing at the measurement set format, which I'm quite frankly not a fan of, and much help from colleagues who are fans of it. And we finally managed to get the data into a format that I could use after only another week's worth of processing. So this is what we finally saw after all that processing. What you see here are just two time series of intensities from 2 separate LOFAR stations, Latvia in the top plot and Ireland in the lower plot. So the two furthest, the 2 stations with the greatest separations. And what you see very obviously is this quite strongly enhanced period of scintillation for about 20 minutes. And it's not quite, but almost simultaneous between both these stations, about 2,000 kilometers apart. Now, at those times, or between those, at the start of that particular period of enhanced scintillation, this is where 3C196 was in the left-hand plot at 1616. You see that particular day, basically right behind the plasma tail of the comet, as displayed in this illustration, which is taken from the Stellarium software package. And at the end of the 20-minute period, we see that it's moved a little bit further across in the tail. Now, it's moved across about 3 arc minutes across the sky during this particular period, which would equate at the distance of the comet to a distance of about 100,000 kilometers. Now, of course, what I've got from each station now are full dynamic spectra covering the full 110 to 190 megahertz range. So in this plot from the Latvian station, we have time along the x-axis there and frequency going down along the y-axis, and you can see also the period of enhanced scintillation where the scintillation is stretching across the full band here. And there are other things in there, but they're mostly artifacts from the system. Looking at the Irish station in the centre of Ireland, then we can see a fairly similar thing. So what I want to do now is just zoom in to some of these to 3-minute segments of this, just to take a look and see what the scintillation looks like in the dynamic spectrum. And this is what we see. So if I take the period at the very start of this period of enhanced scintillation, just a 3-minute chunk, then we can see the regular scintillation itself as a full band pattern, but we also see a curving across the band, this much broader scale structure. And we see it curving towards the left as we go down in frequency at the start of the period. And looking at this 3-minute period at the end of the enhanced scintillation, we see it curving in the opposite direction as we go down in frequency. Now, these are features that I basically have not seen in several years worth of observing IPS. I have seen them in several years worth of observing ionospheric scintillation. And in that particular case, I tend to interpret these things as being likely due to refraction through the edges of a large-scale structure. So if you imagine a very large bubble of plasma moving across the line of sight, then as we traverse the first edge of it, then we would see the scintillation pattern curving one way in the dynamic spectrum. And as we traverse the opposite edge of it, then we'd see it curving the opposite direction. So that's the interpretation that I have from seeing this kind of a structure in the dynamic spectrum. There is one further thing that we can do with these data, and that is to try and map out the intensity pattern in terms of space. So in terms of, instead of viewing it in time, view it in space instead. We have the LOFAR array. We have many stations covering several hundred to thousands of kilometers. So the way we can do this is, if you take a look at the left-hand plot here, then each point on that plot is a LOFAR station, plotted as position relative to the central station, and in a coordinate system where X is the radial direction from the sun and Y is perpendicular to it in the sky plane. And the color code is normalized intensity for a single time sample for all of the stations. And next we can simply overplot the next time, exactly the same, but for the next time sample, and shifting the time sample in space by a distance corresponding to the solar wind speed, which in this case I've measured from the IPS measurements to be about 650 kilometers per second. And then we carry on with the next time sample and so on. And so what we end up with is a sparsely sampled picture of the scintillation intensity in space built up in this way. So here we have 3 panels which cover 3 successive half-an-hour blocks of the data. So we have the tangential baseline on the y-axis in each case, and the x-axis is basically a radial distance. Now, what's very obvious is in the middle plot here, which goes from 1610 UT to 1640 UT, and we can see the period of enhanced scintillation that I've been talking about, and you see very clearly that it appears to have this this diagonal structure in the perpendicular direction, suggesting effectively a drift in a slight drift in space and in time. Now, the solar winds should only be flowing in the x direction here. It shouldn't be flowing in the y direction as well. So the interpretation that there's likely to be here is that this is really reflecting the drift of the plasma tail across the radio source. So this drift, this speed of this relative motion of the plasma tail relative to the radio source, if I measure it from this diagonal structure here, let's take the distance between the top and bottom here, and the time samples from the time series in each case, then that speed equates to about 55 kilometers per second, which is pretty close to what I calculated just by doing a quick look at positions in stellarium. It's quite close to a value of 65 kilometers per second, which I calculated to be the direct motion of 3C196 across the comet tail at the distance calculated for the distance of the comet itself at that time. It's a little bit lower, but that I would also expect because the path of 3C196 is not exactly perpendicular to the radial direction from the sun. So when you correct for that, you would probably get around about the 55 kilometers per second that I measure here. So what about what we were actually looking at? If we were looking at, indeed, we're pretty much looking at the tail, we can be pretty sure of that. But then what kind of structure were we looking at? And here I haven't got exactly very far, but we can take a look at some visible pictures taken of the comet at the time and try and find some pictures. So these are two images taken in Austria by a guy called Michael Jäger, who's an amateur astrophotographer, but he produces some fantastically detailed pictures of these comets. Now, sadly, he doesn't have anything from the night of the 16th of July, but the right-hand side, the left-hand side, sorry, here is the 13th of July. The right-hand side is the 20th of July. The very important thing to note, really, is that even in 7 days, there's quite some evolution of the plasma tail structure from a fairly singular tubular structure. You can just imagine this just tube of plasma just drifting outwards from the comet in this image, whereas in the right-hand image you can see that there's some separation between different plasma streams coming out from the comet. Something very narrow coming up here, and something broader, the broader, more obvious structure here. But even that is a bit more structured than in the earlier picture. After much digging around, I did manage to find a picture taken at 1854 UT on the evening of the observation by a guy called Maroun Habib from Israel, and I took the picture from astrobin.com. So where we were observing would have been very deep, very close to the comet, really right in here somewhere, very, very close to the comet indeed. So, and now we're observing that at around about 4:15 UT, 1615 UT to 1640 UT. So in that particular time, from that particular time to 1854, when this picture was taken, then I estimate that the plasma would have drifted up to around about this region here, in which I can zoom in and we can see, and I've overplotted an estimate, a pure estimate of the likely path corresponding to 3C196 at that time. And you can see that there is a bit of structure in there. There is a possibility of some fainter structure to the side of the very obvious blue plasma tail here, but it's difficult to see very much structure within the tail here. So I need to investigate this further. to see, to try and model a little bit about the density structure within the plasma tail from the measurements we've taken. But basically, this is as far as I've got, sadly, and so here the tail must end for now. But what I can say is that this really represents the most detailed observation of scintillation due to a comet plasma tail taken to date. And there is still obviously much to do, imaging being top of the list. So while the UV coverage of the long baselines is not really enough for snapshot imaging, meaning that direct source position shifts may not actually be measurable despite all this, perhaps phase information may reveal something. And regardless, the field of view, about 5 degrees across, contains several scintillating sources, and at least one of which is not 3C196 itself, but fairly close by, also passes behind the plasma tail, but a bit further down from 3C196 itself. So I need to take a look at that to see if we see the same kind of thing in the dynamic spectrum. And with that, I say thank you very much indeed for listening.
That's great, Richard. Thank you very much. Right on time as well, too, which is I'm very grateful for. Okay, questions. Let's see, any hands raised? I have a quick question for you, Richard. Do you have any constraints on the density of the structures that you were probing with the scintillation?
I don't as yet. I've spent a lot of time building a new weak scattering model for IPS over the last few months as well. But trying to assess the actual density structure is something that's going to take quite some time. So I really don't have much constraint on that, I'm afraid.
Okay, thank you very much. Okay, with that, we can move on to our next speaker. Thank you very much, Richard. That was great. And next up, we have Kenneth Obenberger from the Air Force Research Labs, who's going to talk about passively tracking sporadic E with the LWA using reflections of power line noise. So turning some bad data into good data. Okay, thank you, Ken. Take it away. And Ken, you have 17 minutes. I'll give you a 2-minute warning.
Okay, unmuted. All right. Okay, yeah, so my name is Ken Obenberger. I'm from the Air Force Research Lab. And yeah, so I'm gonna be talking about, two things which are really not very popular in radio astronomy, and that's the ionosphere and RFI. So I thought maybe more appropriate to change my name of the talk, which is change it to RFI and ionosphere, why two negatives make a positive. So really just turning trash into treasure for a radio telescope, that is. But yeah, so I just wanted to point out my collaborators here. So you see some familiar names down here from UNM, Gregg Taylor, Jay Sowell, and then of course, Savin Varghese, who is a graduate student, or actually he just graduated and he's looking for postdoc. So if you're looking for a good student, well, a good postdoc, I have just the guy for you. A lot of the broadband imaging stuff that I'm going to show it wouldn't have been possible if it wasn't for him. So yeah, and of course some folks at AFRL too, which I'm sure none of you even know. So yeah, moving on to the ionosphere. So just kind of give you like a brief summary of what it is, right? So it's just a bunch of plasma in the upper atmosphere that is driven by the sun. So basically, it's a very dynamic radio propagation machine that's like changing, and it's for radio astronomers, it's moving their sources around, it's changing the spectrum, it's doing all kinds of nasty things. But that affects everybody who uses anything, any radio waves really below, L band and below, and probably even higher too. They all see effects from this. So it's something that we monitor for both scientific purposes and situational awareness purposes. And really basically kind of what we sort of do here is to get a profile of the ionosphere, a bottom side profile, you really, what you want to measure is the plasma frequency as a function of altitude. So what you do is you just transmit at some frequency, and then that bounces off the ionosphere once it hits the plasma frequency associated with what you just transmitted. And so then you sweep through frequencies, and then you can sort of build a model of what the ionosphere looks like. And so on the right here, I have what's called an ionogram, and that's a pretty typical, it's pretty typical for what it looks like. It's, sort of this like smiley face here, and then kind of like a droop down. So that's really basically, it almost looks like that all the time, with some sloshing around from atmospheric waves and that sort of thing. But then every now and again, something very crazy happens, and it looks like this, where now all of a sudden, all the frequencies that you see are all piled up at about 100 megahertz, and you don't see anything above it. You just see this blanket at 100 kilometers, yeah, ish. And that's right smack dab in the E region. And so this happens, usually it appears and then goes away. So it's called sporadic E. So because it's sporadic and then it's in the E region. And the way it forms really is actually kind of cool. You get wind shears in this region of the atmosphere. And due to the geomagnetic field, you can get either a V cross B drift or a V dot B drift. And if your wind shear is going two different directions, then all your ions can really collect into one thin layer. And so now you've just kind of made a sandwich, and now you don't have that many more electrons, right? But you've just smushed them all into a really thin layer, and that then can reflect very high frequencies. And so the Digison view of this is just to kind of look straight up and then see what's up there, and that's it. It just looks above it pretty much all the time. It only gets one data point, and that's more or less directly above. So there's been a lot of curiosity. Is like, what is the structure of sporadic E? Like what's even going on here? Because from the Digison perspective, it's just all of a sudden everything goes crazy. So there's some really cool work that's been done in Japan where they have like a gazillion GPS receivers, and you can actually see sporadic E forming and then propagating. And so here on the right, I have this really cool image. So this is like latitude and longitude, and you can see these like really frontal structures, which are sporadic E, and they're moving through right over Japan, and they can see it. But the problem, I mean, that's great. I mean, it's amazing. The work they've done here is really awesome. The only issue is that you don't actually know what the density is because you're integrating through this whole column. So you actually don't have a density estimate, which means you don't really know what the effects are on, say, ham radio communications or any kind of RF communications, really. So that's where the LWA comes in. So for a very long time, for about 10 years now, we've looking at the LWA TV images, you see these things pop up on the horizon. So here you have your Milky Way, right? But over here on the horizon, so this is the horizon of the image, you have this weird blobby structure moving to the north. And and just for reference, this is a local power line. So that's just sitting there, it's not moving. But this junk is moving around and it's drifting north. And so this happens a lot. And anecdotally, it seems sort of consistent with sporadic E. But we didn't do a formal study until like this summer, when I had a lot of time on my hands sitting around my house. So I just like basically watched 2 years of LWA TV. It was because I ran out of Netflix to watch. So I just started doing that. And it turns out that if you take all that data and you say when it happened, you actually get some really, really useful information. And I also wanted to just point out that this little cute little blob moving to the north, that's a pretty tame version. This is oftentimes what it looks like, where there's all kinds of things going on all like across the whole horizon. And you even get a lot of like these narrow band transmitters that are reflecting in. So yeah, it's not always as cute as the one I just showed you. And this is when the radio astronomers, I think, throw away their data because it's so terrible. Yeah, so anyway, so going back to this 2-year study I did, so you just grab all the times where this blobby stuff is happening, and you plot it up, and then you compare it to what Digisons see, and ask, is this consistent with sporadic climatology? And here on the right here, I have plots of the time of day, and then the number of events detected, basically. So Digisons are seeing sporadic E, and then the LWA, these are the blobby things. And yeah, you end up seeing a very similar structure. You have a peak around noon local time, and then another peak sort of later in the afternoon. And it's pretty similar to what the two nearby Digisons see. And then probably more telling is the day of the year climatology, where you get a lot in the summer, like right in the middle of the year, and then a little bit sort of towards the new year, like right around the solstice. So this is really telling us, yeah, this is probably sporadic E. Okay, so now what does the spectrum look like? So we have this really nice new broadband imager on LWA. It's taking 20 megahertz of bandwidth of the entire sky, making all these kinds of cool images. So you can kind of just pick a spot and say, what does the spectrum look like? And you end up getting these really sweet dynamic spectra that are full of structure, and they're a little bit hard to interpret, but there's a lot of stuff going on here. I just want to sort of point out that the upper edge of this, so this is like some sporadic blob. The upper edge of this is sort of where propagation no longer can exist because there's not enough density for it, right? So as your radio waves propagate up, there needs to be a dense enough plasma to refract them back down to us. So the upper cutoff is what we call the maximum observable frequency, which, if we know the location of the sporadic E, is related to the density. It gives us that density information that the GPS doesn't give us. Okay, the other really cool thing about these plots is all the crazy structure in here. And if you kind of look at this structure, it's really wave-like in a lot of ways. It's broadband, but it's like wavy. And the frequencies involved here are really consistent with atmospheric gravity waves, not gravitational waves, but gravity waves, like the ocean waves. And there's these big giant atmospheric waves that propagate across the globe. An earthquake goes off, and then the whole ionosphere shakes across the whole globe. You may not feel it where you live, but the ionosphere where you live is probably seen any giant earthquake or a hurricane or a tornado or whatever. Yeah, and the other thing that's really interesting is now going to the time domain. And if you take some blob and then you look at the timing structure at really high, like fine resolution, you see that it's composed of these little bursts occurring suspiciously at 120 hertz, which just so happens to be twice the operating frequency of the electrical grid. Okay, so what does that mean? Well, now let's look at the azimuthal distribution. Let's take a sort of a threshold and say, where does the brightest blob stuff occur at? And you plot that azimuthally because it's usually occurring on the horizon. So you just grab it from the horizon and say, where is it happening at? And voila, look, it's occurring at all these cities across North America. From Oklahoma City all the way around back over to Salt Lake City. You see the cities, right? You see them there. And that's because there's tons of people there. And so for instance, here's Pasadena here. This is where Gregg lives. And so when Gregg makes his coffee, that triggers his power line outside of his house to make a bunch of sparks. And then those propagate all the way over and then becomes my signal. So thank you for all the people that make coffee and use electricity, because you're making something that's really valuable. You're making one of the biggest radars that's ever existed. And the other thing here I wanted to point out is that there's these really cool areas where there's nobody lives. So Wyoming, Nevada, and then Baja. So if you want to build a radio telescope away from everything, this is kind of a good map. Tells you, and you probably already knew this, right? But yeah, anyway, it's kind of a little bonus. So yeah, right. So what's happening? So power lines are making noise. They go up, they bounce off these little blobby sporadic-y things that are moving around. And the nice thing is that there's power lines, and you go back to this map, power lines all over the whole continental United States and Mexico. So really, it's a really continuous radar. Like there's stuff everywhere. And so, hey, we have 2 LWAs. That means if we could look at one sporadic E structure, it's illuminated by a continuous source. So we can actually look at the plasma. We're not looking at the source anymore. We're looking at the plasma as it moves along. So what I have on the right here is in pink is LWA Sevilleta, and on the in the green is LWA1. And I've just kind of fit a like a smoothing spline to the maximum brightness there. And yeah, so now you can take those two things and you can assume the Earth is spherical, which is more or less right, not quite. And you can ask, okay, where do these two lines cross at? And what you see is that they cross, these two, they cross in Texas, and then they, time is shown in color here, and then they're in Texas, and then they chug along to the southwest. So they're moving to the southwest, and there's also this weird structure in here, and I think it might be real, but we have to remember that we're probably looking at a frontal structure that's propagating sort of this way. And then over here, there's, different cities and things. So it could be that, it's just, one city's brighter than the other, so the centroid moves. Or it could be that as the front propagates, the density is changing. And it just so happens that the distance here between these two bumps is about 100 kilometers, which just so happens to be about the wavelength that you'd expect for what's called a medium scale TID, or a traveling ionospheric disturbance, which is just an atmospheric gravity wave. And then over here, you could probably just ignore this stuff over here, because the two stations really don't have great angular separation for this part. It's really this part that we should focus on. So yeah, it could be some kind of modulation of the sporadic E by the gravitation, the gravity wave, which would be pretty cool.
2 minutes, Ken.
2 minutes? Okay, cool. Yeah, so this is sort of just a plot of where in the United States this is even possible to triangulate the sporadic E using the LWA Sevilleta and LWA1. And then I think it's just kind of fun to show, like, well, what if we had a couple more, right? So we just add a few more on here in various places that I like to go fishing, really. But no, it's really the places that I want to build telescopes. And now you get a really good coverage of the whole, over much of the United States. And now you can really track sporadic E. So it'd be nice if we could just start plopping down. Well, first of all, we really don't know. We haven't verified this, right? Like I haven't looked at these sporadic E moving over a digisonde and say, hey, do I actually know what's going on? So that's the first step, and I think I can do that with the two LWA stations, and just put a digisonde out somewhere. But if it works, I think this would be a really cool way to monitor sporadic E in huge areas. Yeah. And I also want to just point out here that sometimes we do see a pretty high elevation. So this is an event that occurred at like 50 degrees elevation. And these observations are at 38 megahertz. So the geometry there means that the sporadic E needs to be like at least 30 megahertz. Like the plasma frequency needs to be at least 30 megahertz for us to see this, which is crazy. And it's probably the first time anyone's really ever seen anything like that. But the second thing I want to point out is that we definitely see this frontal structure, right? I mean, you can just clearly see it in the two telescopes, this nice frontal structure moving down. It's very similar to what they've seen in Japan, only now we can get density information, whereas this version can't. But we can only do it in places where there's power lines. So the two could work together really well, I think. Yeah, and then I think I'm done. So I'll just maybe, am I out of time? Probably.
Yeah, just out of time, but you can do a quick summary.
Oh, yeah. So anyway, so the summary is it's just like, you know, there's a bunch of anthropogenic noise out there, and it's not, you know, it's not completely useless. So if you find yourself cursing at your screen saying this dang RFI, you just be, oh wait, I know a guy that uses that. So yeah, that's really the moral of the story, is that it's actually kind of useful. Yeah, and I'll just leave the rest of the bullet points. People can read that.
All right, Ken, that was super cool. Thank you so much.
Yeah.
We see those all the time in at Avro, and we just always flag them. So it's glad that someone's been a bit more careful in figuring out what they actually are where they're actually happening.
Yeah.
We have a question in the chat from Surajit Mandal. Ionospheric disturbances have been imaged with the VLA before. Is it possible to image these disturbances with the VLA as well?
Probably. So the VLA, from my understanding, it's seeing ionospheric disturbances in the F region, which is where the most of the plasma is. And so that's where most of your refraction is occurring at for the radio sources that are going through, that you're looking, you know, out in space or whatever. And certainly ionospheric disturbances couple down pretty far, and I think that there's pretty good evidence to show that they couple all the way down to the E region. I guess the big question, and this is where the VLA might really benefit, or any kind of ionospheric disturbance detector, is we don't know if these sporadic E fronts are connected to anything in the F region. For nighttime, there's evidence that that's occurring, but the nighttime ionosphere is very different than the daytime. So we really don't know, and I think that's something that would be really, really cool to look at, is whether it's the VLA or you know, other forms of looking at the F region, to see that coupling if it exists.
Okay, great. We also have a question here from Namir. Namir, you should be unmuted if you want to ask your question.
Yeah. Hi, can you hear me?
Yes, we can.
Yeah. I mean, it's just kind of a silly question, but I presume if you would want stations all over the place, but you really want them you'd want them like distributed like a grid, right? Distributed like for aperture plane. There's no chance you'd want like a log spiral, right?
No, I just need a triangle or an L shape. I guess at this point I really don't know what I want. Right? There's a lot of different ways to do this, and as long as you have, you know, sort of like an east-west baseline and a north-south baseline that are on the order of hundreds of kilometers or so, then you have good, you know, triangulation capabilities. So,
I see. So it's not obvious that you want a grid. You may want something else. Okay.
Yeah, and redundancy can be good. And then, but the further apart your stations are, then the more likely they're not going to see the same sporadic key. But that's fine, because you just build, you know, clusters, I guess. But I mean, I don't know what I want. I mean, I'll take anything anyone has. I'll use it.
Thank
so
you.
Like LoFar, I think would be a great place to try to do this. The stations already exist on those baselines, and they can do all sky imaging, and apparently they've already seen this kind of stuff before. So this is perfect.
Okay, Ken, that's great. We better move on. There's an additional question in the Q&A, but if you can answer that question in the appropriate Slack channel, and that'd be great. And we better move on for time reasons. Okay. So next up we have Sophie Musset from the University of Glasgow. If you could just stop sharing your screen.
Sharing. Yep.
Yeah, there we go. And Sophie's going to talk about the combination of radio and X-ray signatures of solar energetic electrons to study the radio source sizes in the heliosphere.
Yes. Hi. Can you see my screen okay?
We can see the screen just fine, so thank you very much.
Yeah, thank you. Yes, so I'm a postdoc at the University of Glasgow, and I will present here some work that we've done with some colleagues in Glasgow, in Paris, and in Minnesota. We'll talk about combination of radio and X-ray signatures and see how we can look at solar energetic electrons in the heliosphere and at their source in the solar corona, and try to see what we can learn about radio source sizes in the heliosphere. We had a really great first talk that presented all the type of radio emission that we get from the sun. So I will maybe just add a reminder about type 3 radio bursts that are really what we'll be focusing in today. And also explain a little bit what we see with X-ray on the sun during solar flares, and then show the analysis of a particular event that have been observed in X-ray and radio at high and low frequencies. Okay. Okay. So first, just as background, the sun is emitting energetic particles, accelerating particles that are sometimes escaping the sun and can be measured in the heliosphere and can drive space weather. And so we often say like solar energetic particles fill the heliosphere. And this is actually one very topical subject because the investigation of their origin is one of the science objectives of the two major missions that we have in the solar physics field right now that were launched this year for Solar Orbiter and 2 years ago for Solar Probe. So Solar Orbiter is the European mission and Parker Solar Probe is the American one. And so this is a subject that is really investigating a lot right now. And one of the possible sources of energetic particles are solar flares. So what is a solar flare? Have short movie we already saw a bit in the first talk. This is basically something happening that is very sudden and very bright in the solar atmosphere, and we know now that it's a sudden energy release in the solar corona that is due to magnetic field reconnection. Usually we have this kind of cartoon when here you have an actual data. So you can see the atmosphere in EUV in colors here, and this is the surface of the sun. And we see small contours in black, which are the X-ray emission associated with a flare, and the radio source associated very much higher in the corona. What's happening here is that we have in green represented an idea of what could be the magnetic field, very simplified. We assume at some point there was magnetic reconnection in the corona where this is the flare site, and usually this energy that is released will be converted to plasma heating. For example, that's why in EUV the region gets very bright because the plasma gets very hot. And we also have particle acceleration. We can have also plasma motions, other things, but those are the two I'm focusing on. And what's happening then is that we have in particular, electrons that get accelerated would then propagate along magnetic field lines. So some of them will be propagating downwards on those field lines, and they will reach a a much denser atmosphere because they are going down. And this is when they will experience Bremsstrahlung emission that is emitted in X-ray. On the other end, some electrons might also propagate upward. And if in this event, it's shown that we have like magnetic field lines that we said are open, it's actually they are just extending to a very, very high altitude and to the interplanetary medium. And so particles can escape the solar atmosphere. And those particles can be responsible for coherent radio emission, namely type-3 radio burst, which frequency is proportional to the plasma frequency of the medium. Okay, so what can we learn from the X-ray part of these observations? Those are typical observations that have been made in X-ray using the RECI spacecraft. We can do both imaging and spectroscopy. And so what we can see here in the spectrum is that we can usually model the spectrum with two components. Usually at low energy, we have dominant thermal emission, which depend on the plasma temperature and emission measure. And at higher energy, we can see a non-thermal component, which is often modeled with a power law, so characterized with the non-thermal flux and the spectral index. And it's also very common to see this kind of shape in the image where the thermal part is emitted by some kind of loop structure and the higher energy emission is emitted at the foot point where the high energy electrons enter a very dense material. So the X-ray diagnostics are really useful to get some information about the plasma conditions just below the flare site and the distribution of energetic electrons near the acceleration site, which is the flare site. On the other hand, we have these type-3 radio bursts that have been presented before. So you have here, it might be the exact same example that was shown in the previous talk about in the percent frequency decreasing on the y-axis, because that shows when we do that, we see the drift in a positive way over time. This is coherent plasma emission. So the frequency of the radio emission is proportional to the plasma frequency. The plasma frequency is proportional to the square root of the plasma density. So on this plot, plasma density is also decreasing, but as you can imagine, when we are going to higher and higher altitude, the plasma density is decreasing. So this is in this plot, the height is actually increasing. And so we can see those type-3 bursts are produced by electron beams that are reaching higher and higher altitude. They are escaping the sun. And so they are producing this emission at lower and lower frequency over time. So type-3 radio bursts are a very useful tool if we want to trace the propagation of energetic electron beams in the solar atmosphere and even in the heliosphere. And here you see that we have data over many different order of magnitude for the frequency. It's starting at 1 gigahertz and until something like 100 kilohertz. So for the high frequency, we have here data from ground-based instruments, and they are completed with space-based observation at lower frequency. Okay, So I will now go into details about one specific event that is of special interest. And this is something that was observed. Oh, this is not the right date. This is not this year. It was in 2015. Sorry about that. So what we see here first in the two first panel are light curves in X-rays from two different instruments. We have RECI in colors here and Fermi, which is an astronomical X-ray telescope. And we also have a gray light curve here, which is the Gauss light curve showing the low energy X-ray. As you can see, we have quite big gaps in this data. It's because both Gauss and Fermi are orbiting the Earth and experiencing eclipse when they look at the sun. And we are missing actually what we could see as a major event in the radiodynamic spectrum. We have many type 3 bursts here that correspond probably to some kind of peak in the flare. But that we can't really see in the X-ray. But what is really interesting in that is that later type 3 burst or group of type 3 burst here, for which we have some data in X-ray. And actually, if we zoom in, we have a very good time correlation between the radio emission. So we have here one dynamic spectrum from the Orphée spectrograph, which is a spectrograph in France. And we have here the dynamic spectrum of LOFAR. And we can see on both those things, the type 3 radio bursts. And this is corresponding to some increase that we can see in the high energy beam of Fermi telescope. I do not show RECI because it's less visible in the RECI light curves. Fermi is really good because it has a very high cadence light curve. So what we can see is an increase in high energy X-ray emission. It's actually more prominent in the higher energy bands than the lower ones. So it's probably non-thermal. As you can remind that usually the high energy end of the spectrum is non-thermal. In here, we see this very fast drifting. It's almost difficult to see that it's actually drifting in frequency. So those are type 3 radio bursts, but also very high in the frequency range. We have some kind of radio spikes. And we see the low frequency counterpart of this type 3 radio burst in LOFAR. So this is some type 3 radio bursts that really extend over a large frequency range, which is not always the case. So here we have a clear association of X-ray emission, high and low frequency type 3 radio burst. And actually, given the small model that I've shown where we expect the flare is happening, the electrons are propagating downward and upward, it seems like it's not a big surprise, but it's actually quite rare to see such a good time association between X-ray and type 3 radio bursts. So this is really a great opportunity to link what we see in the low frequency radio emission that is really far away from the sun, or at least from its atmosphere, even if it's still inner heliosphere, and to link that to the solar source. Just to have the geometry in mind, we expect, and this is kind of repetition, but we expect the acceleration site to be somewhere in the corona. The type 3 radio burst to be emitted above these acceleration sites and the X-ray to be emitted below. So in terms of density, we expect that the density of the acceleration site is kind of between the density that could be deduced from the radio emission and the density that could be deduced from the X-ray emission. And if we know the density, we kind of have a hint of the height of the acceleration site that is actually difficult to observe by itself. We also have some studies that claim that radio spikes could be coherent emission that is emitted very close to the acceleration site itself. And since in this event we see those spikes, that's actually an additional hint of where the acceleration region could be. So looking at the X-ray data, we have these slide curves, and we can actually do a bit more about this because we have the imaging capability of the RECI data, RECI observations. The problem that with RECI is that the sensitivity isn't good enough to actually do the imaging at the exact time of this small excess. So it has been done a little bit earlier in the flare, but we see a source that is high in the corona. And this is useful because we kind of have an idea of the size of the X-ray emitting region. And then we can also do a spectroscopic analysis. And this is one example. This was done with Fermi. Because the signal is very weak, first we subtracted anything that was here, not the excess, to just identify the non-thermal parts of this excess. So from the thermal plasma, yeah, okay. For the thermal plasma, okay. For the thermal plasma, we can find, and with an idea of the volume, we can find a density that we can relate to the density to the density that can explain the radio emission. And we see good agreement between the lower limit on the plasma density and where the radio actually starts. So this is where the X-ray is, where the X-ray source density is in this frequency mindset. And this is where the radio starts. And so that's actually a very good agreement. We also can calculate the number of electrons that is actually enough to power the type 3 radio burst emission that we see. So that's good. And we have the low frequency radio sources that are observed with LOFAR. And of course, with LOFAR, we can do very good imaging. And this is the centroids of the sources. You can see the drift in frequency as we go further away from the sun. And using that, we can look at the radio source size as a function of frequency that is shown here and correspond to something that we've seen, to trends that we've seen with other data sets. And I will pass quickly on that, but to get an idea of the height, we need to we have the plasma frequency, okay, we have the radio frequency, which is linked to the plasma frequency, itself linked to the plasma density. And then with the density model of the solar corona and in Ionosphere, we can convert all of that into heights. So radio frequencies are a proxy of radial distance of the radio sources from the sun. And so this is the main result, which is that we can follow the source of the radio emission, the size of the radio source emission with the height above the surface of the sun. And this is the measurement here in black with some kind of fit in blue showing the trend. And this is the expected size in red with the size of the beam deduced from the X-ray. And so what you can see that the observed measured size from LOFAR are very much bigger than what we could expect. And how this expectation is actually calculated, we assume the source height and beam size at the source from the X-ray observation. And we assume that the size of the energetic electron beams depends on the expansion of the magnetic field with height. We have some measurements of this. And this is how we make this expectation. Of course, that means that radio source size cannot be explained by the only expansion of the magnetic field, which is something that we already know. So as conclusion and perspective, this event is particularly good one because we see a very good correlation between non-thermal X-ray emission and type-free radio burst, which are both signatures of energetic electrons. And so we can characterize the solar source of escaping beams of electrons that are responsible for the low frequency type-free radio burst. We've seen that the radio source size are larger and increasing also more rapidly with height that we can explain with only the expanding magnetic field with height. And this is probably due to radio wave scattering, which is well known to actually alter by a lot the properties of the radio source size in the heliosphere. And this event is a really good case to constrain the scattering models or scattering simulations that exist. And so I will just add that the combination of X-ray and radio diagnostics of energy particles is really a powerful tool to investigate particle acceleration and transport, but also the plasma condition in the inner heliosphere, such as the condition for the scattering of the radio waves. And this is really focusing with LOFAR on the inner solar radius that will not be reached by the probes such as Solar Probe and Parker Solar Probes and Solar Orbiter.
Okay, thank you, Sophie. That was great. We're sort of out of time, I'm afraid. We have one question. Why don't we just go ahead and have one very quick question? Sergi, do you want to ask your question?
Yeah, so I wanted to ask that, can you please tell what we can learn about the scattering based on the suggestion that based on observation that the source size increases more rapidly with height. So how does scattering change with height? Can you comment on that?
Yeah, I think you have scattering that will at one height explain when the source is bigger than expected, but this is happening over the propagation of the radio waves and over the propagation of the source itself. So increasing is like the source increasing is adding up as the propagation goes. So I think that's why the increasing is just more rapid than just the increasing that you can get from just expanding magnetic field.
Okay, we have to move on, I'm afraid, now because we're out of time. Sophie, there are additional question for you in the Q&A, if you want to answer it there directly.
Yeah.
Okay,
sure.
let's go ahead. If you can just stop sharing your screen, Sophie.
Yes.
And actually, Surajit Mandal from NCRA is our next speaker, as it happens, who asked the last question, and he is going to talk about the first radio evidence of ubiquitous impulsive heating in the quiet solar corona. I'll give you a 2-minute warning.
Thank you. So I will be talking about the radio evidence of ubiquitous impulsive heating in the quiet solar corona. So first of all, I would like to thank my collaborators. Now, I will begin this talk with a brief introduction about the coronal heating problem. So the photosphere, which is the lowest layer of the solar atmosphere, as we all know, is at a temperature of 5,800 Kelvin. In this plot, I have shown how the temperature of the solar plasma varies as a function of height from the photosphere. So as the height increases from the photosphere, initially the temperature drops till you reach the chromosphere, which is the second layer on the solar atmosphere. In the chromosphere, the temperature slightly increases till you reach a very thin layer called the transition region, where the temperature jumps by more than an order of magnitude and exceeds 10 to the power 5 Kelvin. After that, the temperature rises much more slowly and reaches about 1 million Kelvin in the solar corona. It has been a puzzle for many decades now as how the corona, which is much farther away from the photosphere, can maintain its 1 million Kelvin temperature when the photosphere is only at a few thousands Kelvin temperature. It is believed now that the magnetic field which is present in the solar atmosphere is responsible for transporting the energy from the solar surface to higher up in the corona. The magnetic field which permeates throughout the atmosphere is actually rooted in a layer called the convective zone, which is the layer just below the photosphere. Inside the convective zone, there are very violent churning motions of the plasma. The kinetic energy of the plasma is much higher than the magnetic field energy. Due to this, a fluid parcel in the convective zone, when it undergoes its churning motion, it takes along with it the magnetic foot point which is rooted inside it. However, this motion of the magnetic foot point is not immediately transferred to the parts of field line higher up in the corona. This creates magnetic stresses, and that is how the kinetic energy of the plasma in the convective zone is converted to magnetic field energy. Now, the exact details of how this energy is transported to the corona and dissipated there varies from theory to theory. In general, there are two classes of theories. One, the wave heating theories, and secondly, the Parker's nanoflare hypothesis. In this talk, I will only talk about the nanoflare hypothesis. This is a cartoon drawn by Parker. So imagine these are these magnetic field lines, initially uniform, which are rooted at the convective zone. So imagine this is the convective zone, and the other part of the field line is in the corona. As I mentioned earlier, that there are these random motions by which the foot points of the field lines are moved in a random manner. See, this is they have been moved randomly. However, this motion has not been transferred to the corona immediately. So here these parts have been fixed. This creates a very complex magnetic field geometry, and reconnections within this complex geometry can convert the magnetic field energy to heat energy in the corona. Parker postulated that these sort of magnetic field geometries are quite common in the corona. Flares with energies of the order of 10 to the power 24 ergs can happen almost always inside these magnetic structures. And he suggested that such small flares are responsible for coronal heating. Now, these small flares are called nanoflares because they are of the order of 10 to the power 9 times smaller than the larger flares which both Sophie and Seri talked about. Now, although this hypothesis is quite simplistic and attractive in nature, there has been no direct observations of nanoflares till date. The main reason is that these nanoflares are predicted to happen at very small spatial and temporal scales, which cannot be resolved with the current instrumentation. However, there exist few indirect evidences. For example, here I have shown an I have shown an image in extreme ultraviolet taken with the Hi-C instrument. The Hi-C has an angular resolution 5 times larger than the AIA images which are routinely used to study the solar corona. Now, with this high resolution, you can see these complex magnetic field structures which are very much similar to the cartoon I showed earlier drawn by Parker. This suggests that probably nanoflares are actually occurring in the corona, and it is only because of our instrumental limitations that we are not able to observe them. Hence, it is important to search for other probes by which we can probe the nanoflares with the current available instrumentation. Although these indirect observations were a handful in number, these observations have shown that nanoflares can actually accelerate electrons and produce non-thermal electron beams. It is in this context that radio observations can play a very crucial role in probing nanoflares. These non-thermal electron beams, through various plasma processes, can emit plasma emission. As you all know, the plasma emission is coherent in nature and hence is easier to detect than the thermal signatures. Additionally, these are highly impulsive in nature. Because of its importance, multiple searches has been done to find these impulsive emissions. However, these were mainly focused on active regions. By active region, I mean this sort of coronal loops and other bright structures in the UV from which the flares talked about previously by the previous two speakers occur. However, as you can see, it is often happens that the area which is covered by this active region is much smaller than the area covered by the quiet sun. You can see here that there is only one active region, other areas are quite quiet. On top of that, in the last solar cycle, we have many days when there was not even a single active region on the solar disk. However, the quiet solar corona was still hot, and hence it is important to understand what are the physical processes by which the quiet solar corona maintains its high temperature. Now, what are the issues which limited the study of these impulsive emissions in the quiet sun? First of all, to study these faint impulsive emissions from the quiet sun, it is necessary to image the quiet sun at high fidelity, at high temporal and spectral resolution. However, the imaging algorithms which are necessary to properly model the extended nature of the quiet sun was only available recently. On top of that, to properly model the quiet sun at high temporal and spectral resolution, it is necessary to have a dense instantaneous sampling in the UV plane. Instruments capable of achieving this only came online recently. Now, with the new instruments, we have to solve a very different problem. The data which these instruments provide are very voluminous in nature. For example, the MWA, which has 8,128 baselines, produces about a terabyte of data every hour. And analyzing this huge data manually is highly impractical. To solve this problem, we have developed an automated imaging pipeline to image the sun with compact arrays like MWA. Pipeline is called AirCars, and the imaging dynamic range, which is produced by this pipeline, is regularly 10 times higher than the earlier works, and in favorable conditions can produce images whose dynamic range is 100 times higher. Now that I have convinced you that with the availability of modern instruments and modern software, we are in a position to image the quiet sun at high dynamic range, at high spectral and temporal resolution, we are all set to search for these impulsive emissions in the quiet solar corona. On top of that, we also wanted to do a robust statistical characterization of these emissions. We chose to work with MWA data from 27 November 2017. The sun was very quiet on that day. There was only one active region, which you can see here on the solar disk on that day. There was no X-ray flare or radio flare reported on that day or the neighboring 2 days. Hence, this data set was very well suited for investigating the quiet sun. I imaged 70 minutes of data at 4 frequencies at 0.5 second cadence. AirCars was used for this imaging, and a total of approximately 33,000 images were made in this project. I extracted the flux density time series from these PSF size regions, which are used to tile the entire sun. And these flux density time series were used for further work. Now, let me define a quantity called FIT. So FIT is the flux density of patch I, by patch I mean the small regions, at time t. This average Fi is the median flux density of patch I. And delta F by FIT is equal to FIT minus average Fi by average Fi. I combined all measurements of delta F by F for all patches and all times to produce this histogram. It is evident from this figure that this histogram has a power law tail, which is evidence that there is significant non-thermal emissions in the data. I would like to point out that we have been able to lower our detection thresholds by more than 2 orders of magnitude than which was possible earlier in similar works. And that is how we have been able to detect this large number of non-thermal emissions. These non-thermal emissions are highly impulsive in nature. Most of the events which we have detected have temporal widths of 0.5 seconds, which is equal to our instrumental resolution. And we hypothesize, and there might be many more such events which have widths even less than that. We also hypothesize that the extremely impulsive nature of these emissions might be the limiting factor why these events were not detected in earlier searches, as such high resolution data were often not available. A key necessary condition for these emissions to be important for coronal heating is that these emissions should be ubiquitous in nature. To investigate that, I have plotted here their fractional occupancy distribution. By fractional occupancy, I mean the fraction of observing time for which we have detected an event from these patches. It is clear from this image that for every single patch on the sun, we have detected these impulsive emissions. Sorry, I will to also point out that this red circle actually shows the optical disk of the sun. Now, although qualitatively these results match for the 4 frequencies in that for every single patch we have detected this emission, the median, however, varies from frequency to frequency. The median fractional occupancy ranges from 3 to 7% for this data set. Now, it is a very common question to ask, how common is the ubiquitous nature of these impulsive emissions? To investigate that, we have analyzed a very different data set, which was observed 2.5 years after this observation, which I just showed earlier. Again, we find that these impulsive non-thermal emissions are present on every single patch on the sun. It's black here, black circle shows here the optical disk of the sun. Now, although there is this qualitative similarity between these two very different days, quantitatively, there are some stark differences. I said earlier, the median fractional occupancy was for this data set ranged from 3 to 7%, whereas the median was always greater than 10% here.
2 minutes, Surjit.
Yeah, thank you. Now that I have showed you that it is now possible to detect and robustly characterize these emissions, and we have done that in the low frequency millimeter wave band, we want to expand this study across a wide range of frequencies spanning 80 megahertz to 15 gigahertz. Using this wide range of frequencies, you'd be able to probe the transition region, the base of the corona, and the slightly mid corona. We would like to identify the counterparts of these events in other wave bands like the extreme ultraviolet or X-rays. We are also trying to study the temporal, spectral, and spatial nature of these events. By spatial nature, I mean the morphology. How do they look like in the image plane? The final goal is to quantify the number of these events as a function of height. How does the number or the statistical distributions vary as we are probing different heights on the solar atmosphere. We want to get the emission mechanism using wide bandwidth observations. We want to quantify if they are from plasma emission origin, or they have gyrosynchronous emission, or are they free emission. We want to quantify the energy dumped in the corona due to these events using multi-wavelength studies spanning from radio, UV, and X-rays. The final goal is to understand the importance of these events in coronal heating. With that, I will stop and take questions. Thank you.
Thanks, Sergi. Very exciting work. Question in the Q&A for you. If the nanoflare emission can be observed in the weak radio spectrum, can we get any evidence for the formation of plasma cavity shells as a result of the incoming nanoflares due to the plasma present in the immediate surroundings of the sun beneath the solar corona?
So what I heard from the question is that do we detect the plasma cavities due to incoming nanoflare electrons? Is that the question?
That's the question. You can also click on the Q&A button yourself, or if the speaker wants to speak, I can unmute them. If you want to click on the Q&A button at the bottom of the screen, you'll see the question there also yourself.
Yeah, I got it. Yeah, so actually, so right now we have only worked with the radio data, which does not have enough resolution, but we are trying to find counterparts of these emissions in other wavelengths, in UV and X-rays, and hopefully we will be able to get some answer on that. Right now, I do not have any observation evidence for this.
Okay, another question. Are there any follow-up observations planned with UGMRT or the VLA?
As I mentioned, we want to follow these observations with spanning 80 megahertz to 15 gigahertz. The higher frequency ones I plan to observe with the VLA band. Mm-hmm. I have not thought of the UGMRT, but we can definitely try to observe with that as well.
I have another quick question as well too. You mentioned the plan to try to get multi-band observations to constrain the energy, which obviously is very important because this is the big open question you're trying to address. But you also previously mentioned that observations in the UV and X-ray have never been able to detect flares of this energy and cadence. So how will that actually eventually happen?
So I will just try to see if I have the slide here in my future work. Yeah, I got it. So I will again share my screen, and let's see if I can answer your question. So this is a very new result which we are doing just now. Here are the brightest events which we have found in our data set. And these are the radio contours. And as you can see, they are very well aligned with these UV brightenings. And so we believe that these are the UV counterparts of these impulsive radio emissions. And using the UV analysis, we are trying to estimate their energies. So we are yet to find counterparts of the weaker events. We are trying, and let's see what happens.
Okay, great. Well, that's very exciting. Okay, thank you very much again. And thank you to all our speakers for a great session. I just want to remind you all of the coffee session, which you can access in the PDF document, which has a Zoom link, which is happening right away. And another reminder as well to please submit lightning talks if you have results to share. Okay, thank you all. And we shall see you in the coffee session shortly. And